Okay, hello and welcome. This is going to be our project help video. So for this project, you're going to create 4 visual sequences and then fill in some tables and answer some questions about them. Whether or not you actually turn in the patterns as well is up to you, but I really need to just see the tables filled in. So with this video, I'm going to hopefully help you understand how these patterns are constructed, and explain what is meant by recursive formula and a few other things. Alright, so how do we draw nested squares? So you can read this description of nested squares here, but essentially you're just going to the midpoint of each side length of the square, and that becomes the new vertices for the smaller square inside of that square, nested inside. Alright, so I have created the first 1, 2, 3, 4, 5 iterations of this nested square. So let's talk about how we can fill in this table. So first off, square number 1 was that big red square. It was specifically designed so that it would have a perimeter of 40, just like the problem says. In order to have a perimeter of 40, it needed to have side lengths of 10. Divide those by 2, we get 5 there. And then partial sum means just keep adding up this row up to the current square. So we're only at 40 here. But by this one here, we're going to add in this next perimeter. Okay, so how do I find the length of this blue line? Well, I've got to do a little bit of the Pythagorean theorem. We said this length down here was 10. And that halfway was 5. So I've got a little 5, 5 right triangle that I can solve for the hypotenuse to get the length of this blue line. If I do that, 5 squared plus 5 squared equals c squared, and solve, I will get, it is 5 root 2 for the length of this blue line. Okay. So this is now 5 root 2. I'm going to fill in all the rest of these. Let me just pause it real quick. Then we can talk about the formulas there. Alright, so here's this table filled in. Again, my kind of quick explanation of how I found these side lengths is you have to divide the previous side length by 2 to find the legs of the triangle, and then do the Pythagorean theorem to find the new side length, and then you repeat. Perimeter is just one side length times 4. Okay, so do your best to be able to create this table, and maybe even go further with this table and with your diagram. I know I could fit still several more squares inside here before I ran out of space. Alright. So what is a recursive formula? That's what problem number 2 asks us. So a recursive formula tells you how to start with the n-1 term and go to the n term. So this is the previous term. How do I go from the previous term to the current term? So we got to figure this out for the perimeter. So I'll give it away. It is a geometric sequence. But what am I multiplying by each time here in the perimeter? How do I go from 40 to 20 root 2 to 20 to 10 root 2 to 10? Well, each time I am taking the previous term and I am multiplying it. Well, let's just look at the part without the root 2 first. So how do I go from 40 to 20? It's got to be something over 2, and it's got to pick up a square root, so it's square root of 2 over 2. And that's how I get a sub n. So a sub n equals the previous term times square root of 2 over 2. Okay, now the explicit formula, now we have to bring in what our initial term was, the 40. So, well, we'll keep just calling it a sub n equals our first term 40 times our rate, which is root 2 over 2 to the power of n minus 1. All right, now to find the nth partial sum, we have to recognize that this is a geometric series here, so we can use the sum of a geometric series formula to figure out a formula here for number 4. And that formula is a sub 1 times 1 minus r to the n over 1 minus r. Let's fill in the values from this problem. So our first term is a 40 times 1 minus root 2 over 2 to the n over 1 minus root 2 over 2. Okay, and that can probably be simplified, but I'm okay with just leaving it like that. All right, if this continued on forever, what would be the sum of the perimeters of all the squares? So would this be finite? Well, to figure out if it's finite, we need to see if the square root of 2 over 2, which is our rate, is less than 1. Well, this is equal to about 0.7, so that passes the criteria for a converging geometric series. And the formula for the sum of a convergent geometric series is just a sub 1 over 1 minus r. So a sub 1 is a 40 divided by 1 minus 0.7. When I do this in my calculator, I'm going to actually plug in square root of 2 over 2, so I get all of the decimals for that 0.7. I'll do 40 divided by 1 minus second answer. I get 136.6, we'll say. All right. So I know I basically did this whole first one for you, but that's not going to be the case for the next ones going forward. Let's look at the Fibonacci spiral. So for this one, we start with 2 small boxes, and then we just keep, so those are stuck together. So now this becomes one side of a square that's attached. Now together, this has a side length of 3. So if I want to make that into a square, I got to get 3 off. Now if I want to add another square, I got to look at how long this side is. It's 5 units, so you go 5 down, 1, 2, 3, 4, 5. This next one, I'd come out, this is 8, so 4, 6, 8. The next one after this would be 8 plus 5. But I think you're getting the gist. And then at the end, it's kind of fun to put a spiral that goes through all of these boxes. This is actually what a lot of seashells end up looking like. They follow this Fibonacci spiral. Okay, let's fill in some stuff to that table. So what's the recursive formula for the Fibonacci sequence? So any term, a sub n, is equal to the sum of the previous term and the term before that. But for this to work, we need to say that a sub 1 equals 1 and a sub 2 equals 1. And then we can find any other number, a sub 3 and up. All right, so let's write out the first couple terms of the Fibonacci sequence. So 1, 1, 2, 3, 5, 8, 13. And then this just wants us to shift everything by 1. And so the n plus 1 means you actually move everything one cell to the left. So this becomes 1, 2, 3, 5, 8, 13. The next one would be a 21. All right, and now this is asking us to divide these two columns. So you're finding the ratio between any number in the Fibonacci sequence and the number right before it. So this is a 1, this is a 2, this is a 1.5, 1.6, 6, 1.6, 13 over 8, gotta plug that in, 1.625, 21 over 13 is 1.615. So we are converging to a number here with this ratio here. And that ratio actually ends up being the golden ratio. So what value is it approaching? Well, it's approaching the golden ratio. What is the golden ratio? It's about 1.61, and it gets this symbol here for the golden ratio. I think that's a phi, but I'm not sure. All right. I'm going to let you try these. I think you'll find them very interesting. It's a very special property of the golden ratio that's being investigated here. Okay, let's look at the von Cook snowflake. So to create the von Cook snowflake, you need to start with a big equilateral triangle. Here, I started one here, but I'm going to redo it, actually. So we start with one big equilateral triangle. And then each of the line segments, and there are 3 line segments here, you erase the middle third. So the middle third of each line segment. And then you replace it with another triangle that juts out. And the very first time you do this, you get this kind of Star of David looking thing. Zoom out a little bit here. All right, so that's one iteration of the von Cook snowflake. So before we did any manipulations, it had 3 line segments. Each line segment was 3 inches long. I know that because the whole perimeter was 9. And then the perimeter was 9 here. But when I added in these little zigzags, it gets longer. So with those zigzags, we're up to 12 line segments. And each of those line segments is only 1 inch for a total of 12 inches. All right, if we do it again, we gotta get on our eraser. Gotta get rid of the middle third of every single line segment you see, which there are 12 of, and add another little triangle on top of that. All right, and then to do another one, you got to come along to all of these line segments, and there's 48 of them this time. Erase that middle third and add in this little triangle. And we actually have a pretty good picture of what that would look like up here as this keeps going. Eventually this just gets like almost really fuzzy on the outside as you have all those tiny, like microscopic little triangles zigging their way around this snowflake. All right, so I said this had 48 line segments. Each was only a third of a unit, but 48 times a third is 16 inches. So as this gets more and more fuzzy, so to speak, the length gets longer and longer. Will it grow forever, or does it eventually plateau? That's what we're trying to figure out. So recursive formula for the next line segment. So a sub n equals the previous term, a sub n minus 1 times 4. Length of the line segments is a sub n minus 1 times a third. And then for the perimeter, we got to multiply these two. I'll just say multiply and then simplify. And then let's see if you can write the explicit formulas for those. Number 6, I will tell you this now. The perimeter for the infinite Van Cook snowflake is infinity, which is kind of amazing because it's still like a finite area, but the border is so fuzzy that the length of that border actually tends to infinity. A pretty trippy thing to think about. All right, and the last one is Sierpinski's triangle. With this one, we're drawing a triangle and then cutting out the middle upside down triangle each time, leaving 3 triangles remaining, and then we're cutting out the middle upside down triangle of each of those. And this eventually will get rid of the entire triangle. So this tends towards 0 with the amount of the triangle that's remaining. So it's going to go 1, 3, 9. Area. Well, if the whole thing at the beginning is 100, these triangles split it into fourths. So we're removing 25. And then we're keeping 75. And then that 75 will be split into fourths. We'll get rid of 18.75 and keep the rest, and so on. Yeah, I'm just going to let you try this one on your own with very little help from me. I think you guys can do it. I'll call that good here, so hopefully that's a good start for this. Not looking for perfection, but that you at least try your hand at writing your own recursive formula here, and maybe try to figure out the area after infinite iterations, although I think I kind of gave that away, that it goes to 0. But can you prove it? And then here's another recursive formula to write. Okay, I'm going to call it good there. Have a great rest of your day.